Up to this point, our study of light has really focused on two different phenomena. One being reflection, the ability of light to basically rebound off of a surface, and two being refraction, its ability to bend as it moves from one medium to another. But the thing is that all of our analysis up to this point has been treating light as though it is a ray, as though it can travel in these straight line paths at all time, which is perfectly acceptable for everything we've done. But what we're going to do today is look at an experiment, arguably one of the most important experiments in all of physics, that's going to demonstrate to us that this analysis that we've been conducting so far, well, it's somewhat incomplete. For thousands of years, physicists and philosophers had been debating what is the true nature of light. Light is something we see everywhere, and it's very fascinating to us, but what exactly is it, and how exactly does it move through space? Because that's kind of hard to perceive. Well, the main idea, the one that had been really predominating since really the ancient Greeks, was that light was made up of particles, these little you can think of kind of like light bullets or balls that would move in straight lines, much like a lot of the things we learned about with mechanics, with classic Newton's laws, that would move in these straight lines until they encountered a piece of matter or something along those lines, and then they would bounce off or they would absorb or something along those lines. And this was a very old theory, like I said, thousands of years old, with many supporters, including most notably Isaac Newton, which doesn't really, reflect on whether it's correct or not, but that did give it a lot of extra weight. Now, there was a big issue with this theory, though, which was one we've already discussed with Fermat's principle, that light always takes the quickest, or the path that requires the least amount of time, between 2 points. But how does light know to do that? Because light does not have a brain, and this model of light can't really explain that. Additionally, in about the 15 to 1600s, another model of light began to be proposed, and this was known as the wave model of light, which said that light does not move as a particle, but instead moves as waves, as these fluctuations with extremely small wavelengths. Now, this could explain the issue of Fermat's principle, but it could also explain all optical phenomena, reflection, refraction, diffraction, polarization, all of these things, many of which were actually not very studied at previous times, would start to raise some holes in the ray model because it could not support all of these different phenomena. But there was also an issue with the wave model too, because waves, as we learned with mechanical waves, they require a medium to move through. Remember, it's not really the matter that's moving, it's this energy and this momentum, and what exactly is propagating that if light is a wave, because light can travel in a vacuum. And so there was a lot of confusion on how exactly light should be treated, and so in 1801, a physicist by the name of Thomas Young decided to conduct an experiment that he designed that would help try to solve this problem and really bring to the fore, is light a particle or is it a wave? Which one is it? Now, Young's experiment was known as the double-slit experiment because it involved a screen with 2 slits in it. And these slits were very, very tiny and very close to each other. And when we say tiny and close to each other, we mean smaller than a millimeter in width and smaller than a millimeter away from each other. And what Thomas Young did was he basically said, all right, we're going to take a light source, we're going to point it at the screen with these 2 openings in it, and we're going to allow that light to travel through and then hit this screen right here. And the question is, what are we going to see on that screen? So, just to make sure we fully understand, this is kind of an overhead view, and this right here would be what we would see if we looked at it from like head on. So currently we don't have the light going past this yet, so we're not seeing anything on this screen. Well, if light behaved like a particle, well, when it hits this barrier, a lot of it is going to just basically reflect backward, but with the light that is able to go through these 2 openings, well, it's going to continue on in its straight ray-like path. We would expect it to basically just do this, and we would visualize this as 2 bright spots on the screen. Now, if we were to graph this here, we might say that, okay, so this is basically showing us the position on the screen and the intensity of the light that is basically interacting with it. And we would get two bright spots right here on either side of the central point. We would have a dip. It might not go quite to zero here because some of that light might be bleeding across a little bit. We're going to get two big bumps, and then it's going to trail off to zero as it goes further and further away from this point. So this is what it would look like if light behaved like a particle. But let's say we did the same experiment, but light behaved instead not like a particle, but like a wave. Well, what exactly would it do when it encountered these two slits? Well, remember, earlier in this unit, we talked about what waves do when they encounter an opening, or an aperture, that's about the same size as the wavelength. We have the wave hit this basically barrier, and what we remember is we analyze it using Huygens principle, which was created in about the 1600s. And essentially what's going to happen is every single point on this wavefront is going to act like its own little spherical wavelet, creating its own new wave. Now all of these on either side of the barrier, they reflect backward. But this right here in the middle, it can continue on straight forward. And because there is nothing on either side of this wavelet except for itself, well then it's going to end up creating a spherical wavefront rather than a flat wavefront. And so, at this point, what's going to happen is this new wavefront is going to become its own source of spherical wavelets. We draw the tangent line to all of these, and we notice that they are still making this spherical pattern because on the edges we still don't have a continuous line flattening it out. And this will continue on forward into this spherical-like spreading, and this is known as diffraction, the spherical bending or spraying out of a wave through this opening or aperture. So if light is a wave, when it hits these two slits, it should diffract through each slit. So if we look at the top one, we're going to get something like this. And if we look through the bottom one, we're going to get something like that, where these red, dark red, and light red lines are showing us pretty much the crests and troughs of the waves respectively. Now, if we do both of these at the same time, we get something that really hurts our brains a little bit, and it becomes really difficult to know, okay, how exactly is this going to look on the screen? But what I want you to focus on is let's look at this middle line right here, and what we notice is in this region, going straight down the middle, we have red and dark red, or crest and crest matching, and light red, or trough and trough matching. And we have two waves interacting or interfering with each other, and the crests and the crests line up, the troughs and the troughs line up. Well, that means we're going to have constructive interference, and we're going to get a bright spot right here in the middle of the screen. Not offset of the two slits, but right in the middle. And we will actually see, if we look at this picture, there are other points along here where the crests line up with the crests and the troughs line up with the troughs, and we once again have constructive interference. Now, they are less bright as they get further and further away from the center, but it is still constructive. Additionally, we have areas where we actually have crests and troughs hitting each other, and that's going to create destructive interference. So we're going to get these bright, what we often call fringes, kind of like the fringe on a rug. We're going to get these bright fringes with these dark fringes in between, showing us constructive and destructive interference, respectively. So if we were to graph this, we would get something along this lines, where basically we have a nice, bright, intense spot in the middle. Then we're going to have some brighter spots going outward, but between each of these, the intensity goes all the way down to zero because of the destructive interference that's happening between every single bright spot. Now, this is somewhat complicated looking, and it's often known as an interference pattern. That is usually the name for this series of bright and dark spots. So when Thomas Young conducted this experiment, well, what did he see? Did he see two bright spots, or did he see a series showing that light was either a particle or a wave, respectively? And when he did it, he actually did see this interference pattern. And this was the first definitive evidence that light must be traveling through space as a wave. Because if it was traveling through space as a ray, it could not produce this. Therefore, our ray model of light, which works in many circumstances, is just that, a model. It is incomplete. Light actually travels through space as a wave. And this is therefore the first definitive evidence of the wave model of light, which is the basis for what's often called physical optics or wave optics, which lends itself to a whole new realm of phenomena. And it's just based on the idea that light travels through space as a wave. And we know now that light does this because it's composed of self-sustaining electromagnetic waves that don't require a medium. But one, we didn't actually realize that light was this self-sustaining electromagnetic wave until about 60 years after Thomas Young did his experiment with James Clerk Maxwell. And additionally, we didn't really understand that light didn't require a medium, or at least there was a lot of confusion about that, till almost 100 years after Thomas Young completed his experiment. And one important thing to note, though, is that treating light like a ray is often the correct thing to do. The only time it matters is when we are dealing with situations that are involving openings or objects that are extremely, extremely tiny. Because remember, we're not going to see a lot of these effects unless we're starting to get to the order of basically the wavelength of light, which is very, very small. So if we're dealing with anything that is greater than a millimeter in size, it is totally acceptable to simply go along as though light travels as a ray. If we're dealing with smaller situations like that, though, we need to start making sure we think of it as a wave. Now that we have a conceptual basis for this, though, we want to be able to analyze this interference pattern mathematically, because we're going to learn that it actually allows us to determine a lot of things about light sources that we would have had a difficult time doing previously. So looking at this interference pattern, let's go ahead and get some terminology down. This central point here is known as the central maximum, this bright spot here, and every subsequent bright spot is simply known as a maxima. All the dark spots are known as minima. And what I have labeled here is m equals 0, 1, 2, and 0, 1, 2 are what are known as the diffraction order. Basically, it's telling you where in the pattern are you looking. The central maximum is called m equals 0, that's its order. The first bright spot on either side is m equals 1, the second bright spot on either side is m equals 2, etc. But to be able to analyze this, we're really just going to focus on this m equals 1, the first bright spot outside the central maximum, because if we do that, really all the other ones can be analyzed in a very similar fashion. So I've gone ahead and zoomed in on this picture here, and what I want to focus on is the fact that if we look right here, this would be where the point sources of these two wavelets are as they go through the slits. And additionally, this point right here, so this would be where your central maxima is, and this will be the m equals 1 maxima, the first diffraction order. So I'm going to go ahead and actually make this a little reduced so it's a little easier to see. And what we're going to do is we're actually going to go ahead and draw the two waves that go along this path. So rather than have this really busy picture, we're just going to focus on this. So I'm going to go ahead and actually get rid of that for a second. And let's go ahead and start analyzing some details here, start noticing some things. The first thing we're going to see is that we actually have one triangle here. Now let's go ahead and define some of the things of this triangle. So it goes from this purplish line here, goes from the central maximum, which is located at what we often say is position y equals 0 on this graph, to the first maxima, which is at y equals 1. So that is this right here. It's the distance between these two bright spots. L, this light blue line, shows us the distance between the screen and the other screen, one of the slits and the one that it's being projected onto. And additionally, we're going to draw from the center to this point, and we're going to say that this is an angle theta 1. But now we're going to analyze the situation a little differently. What we're going to do is we're going to say, okay, if I look from this source to where it hits this first maxima, and this source to where it hits its first maxima, we're going to call this path R1, you can kind of think of it as like ray 1, and path R2, and these are the distances that the light is traveling from one screen with the slits to the other. And these are not going to be the same distance. Now, if they were hitting this central maxima point right here, they would be the same distance. But because we are one maximum up, well, they are slightly offset. And when is constructive interference going to happen again once we move past that central point? Well, it's going to become destructive interference when the crest and trough line up. And then when we reach the first maxima, that must mean that the crest and the crest are lining up again. So therefore, the difference in length of these two paths is one wavelength of light. Additionally, so that's one side of a triangle. Additionally, we have as the hypotenuse of the triangle this distance d, which is the distance between the two slits. It's going to be very, very tiny. And I'm going to go ahead and draw a perpendicular line here from this source down to this path so that I have a right triangle right here. And why exactly did I do that? Well, the reason we have to keep in mind is that the distance between these two screens is going to be on the order of meters, probably more than a meter. And the distance between these two slits is going to be really tiny. In fact, it's going to be smaller than a millimeter. So essentially, L is much, much greater than D. In fact, it's probably over 1,000 times greater than D is, meaning that this triangle right here is going to be super, super stretched. And additionally, these rays are not really going to be like this. Really, they're going to look way more, basically, almost practically parallel, and this would be even more extreme the more we stretch it out. So in other words, we can basically treat R1 and R2 as though they are parallel with each other, because they're so stretched out that, there's only one wavelength difference. That wavelength is really, really tiny. And if that is the case, well, let's keep in mind a few things. This right here, this angle theta 1, goes from this horizontal line to this. Well, that's going to basically match both R1 and R2 because they are practically parallel to each other. Now, is this a simplification? Yes, but really not much of one because of the fact that this is going to be so much, much, much greater in distance L as compared to D. Well, if I have done this, let's look at this situation right here. What we have is we could say, well, this right here is theta 1, but between this yellow line, which is parallel to here, and this green line, which is perpendicular to here, well, this must be 90 degrees. And if that is 90 degrees, and this is 90 degrees, well, then this, theta 1, must be the same angle here, theta 1. So we've actually created two different triangles here. One is this side right here, which is the wavelength, this side right here, which is the hypotenuse in D, with theta 1 as this angle, and another one with L as this length, y1 as this length, and theta 1 as that angle. And let's go ahead and do some basic trigonometry. Let's say that for this first one, sine of theta 1, which is opposite, or lambda, over hypotenuse, will be D. And additionally, for the other triangle, let's say tangent of theta 1, which is going to be y1, or the opposite over the adjacent, which is L. So at this point, we've actually created two different equations that allows us to compare a few different things. One, the distance between the screen with the slits and the screen the light's being projected onto. Two, the distance between the slits. Three, the distance between the bright spots. And four, the wavelength of the light. Now that wavelength of the light is hard to figure out, so this actually gives us a way to figure out what that wavelength is for a particular light source by analyzing all these other distances. And if we have those three, we could basically plug them into these equations by first solving for theta 1, plugging it into the other equation, solving for lambda. But the thing is, though, is that we could actually make this a little bit easier, because what I'm going to show you right now is here is a graph of sine of theta, where theta is in radians, and this shows you how it goes, between -1 and 1. And what we're going to see is if I put on top of this a graph of tangent of theta, in this tiny little region right here, you'll notice that, one, it's basically a straight line, or y equals x, or really we could say y equals theta. And additionally, sine of theta and tangent of theta appear to be identical. And this is something that is known as the small angle approximation. Essentially, if we have an angle that's less than about 0.2 radians, or approximately 10 degrees, then theta is actually equal, or pretty much equal to, sine of theta, which is pretty much equal to tangent of theta. Is this a mathematical trick? Yes, but it's a very useful one, telling us if the angle is tiny, we can say these are all equivalent. And keep in mind, these triangles were really, really stretched out. So that theta is going to be incredibly, incredibly tiny, meaning that we can actually say, as long as the distance between those two screens is way bigger than the difference between the slits, well then these are essentially identical. And we can say lambda over D is equal to y1 over L. Now I've gone ahead and multiplied the L across to give us an equation that you're going to see known as the double-slit interference equation, that y1 is equal to lambda L over D, where all of these are basically measured in meters in order to be consistent, where y1 is the distance between the central maxima and the first bright spot or fringe. Lambda is the wavelength of light, L is the distance between the two screens, and D is the distance between the two slits. But the thing is maybe you don't want just the first bright spot. Maybe you want to be able to pick out the second or the third or the fourth, etc. Well, what's the only difference between each of those points? Well, it's simply the fact that from the basically central to the first point, that essentially you've got one wavelength difference. If we go to the next bright point, well then one path is 2 wavelengths greater, third bright spot 3 wavelengths greater. So essentially we can change this very quickly by just putting m lambda here, where m is the diffraction order. So meaning that do we want the first bright fringe, the second, the third, the fourth, whatever, keeping in mind that that central one is y equals 0. So what are our takeaways on Young's double-slit experiment? 1, can we describe the setup, the potential results for either a particle or a wave, and the conclusions of Young's double-slit experiment? 2, can we describe the impact of this experiment and how it allows us to view the true nature of light, that it travels through space as a wave, not as a particle? And 3, can we mathematically analyze situations that exhibit double-slit interference, keeping in mind that equation of y sub m is equal to m lambda L over d?